you're on your own and you're trying to read the math text, it's not the easiest thing in the world to read, but some of my students are doing it. And I heard this yesterday. A property, A raised to log base A of M. Now, can someone tell me, that's a property in your textbook, I think. Can anyone tell me the result? It's M. And what makes it M is, are these two bases the same? And I quickly say that if they're the same. If they're not the same, we've got an issue. But in this case, they are the same. Can anyone tell me before I leave this, where did this property come from? You know how I teach. I know where things came from. Anyone tell me, where did this formula come from?
The inverse.
Inverses. There's an a to the x. We'll label it as f of x. And there's another function involved here. Let's call it g of x. Log base a of x. And if you form a composite, it looks like this. In other words, you're placing g into f. So if I place g into f the way they are labeled, please tell me, would I end up with this for a composite? Yes or no? If I place this g of x into my f of x, does it look like that? Yes, no? And what about these two? And I think Jonathan told me they're inverses. So what should that composite always be equal to if they are true inverses? X. That's exactly where this came from as a property. Now, if you see it on the exam on Friday, I don't want to, I'm not trying to trick you when I do these problems on the exam. But if I saw one that's just straightforward like this, 3 raised to log base 3 of 19. Can I immediately give the answer? Does the formula support this? It's 19. If I ask you E raised to ln of pi, can I say immediately that's pi? Am I still making use of this property here? As long as things match up? Okay, so I can easily say that. Now, did I bring in something else here I heard also being mentioned yesterday? Yes, I did. Where was it? Oh, yes. On the side here. I heard this. Log base A of x is equal to y means what? Like a definition. What does that mean? Definition? Anyone? Log of y base x, base a. Log of x base a is equal to y. What does that mean?
It's equal to
It means a raised to the y is equal to x. Restriction? There's a restriction here on the x. The x must be greater than 0 for a log. And that's where I got into those domain problems. Asking for the domain. You see a log and I ask you for the domain on the exam, which I will on Friday. Then this statement here will help me. For example, I'll just reflect you back to yesterday. You saw this. I gave you a function, f of x, and it's equal to, find it right quickly, yes, log, and inside here is x squared plus x. And I'm asking for only the domain, no steps required, just domain. And the property right above there, or the definition, tells me right quickly, this part must be greater than 0. So it means x squared plus x must be greater than 0. Now, how would you deal with that? How would you finish it? That's what it means. Then how would you finish this up to find the domain, find the x? Anyone?
Factor it out.
Factor it out first. They got a common factor of x. Divided this, greater than 0. I'm not gonna finish it up completely. More than likely, most students would be trying what now? Sign analysis. The critical numbers. Just a little recap here that I thought about, and you can finish that up. What else did I look at here? Oh, I did. One more item, I think it is. Here we go. Someone mentioned on one of the handouts, there's a Ramsey, you had this. Suppose for some reason I want to change the base. I don't like the base that the log has been expressed in. I want to change the base for some reason. Now, I'm going to show you the formula that's on your handout. It says log base A of M can be, if you wish, change it to a different base if you do this. That different basis will be base B. Log of M base B divided by log base B of A. I can show you where that came from also, but let's accept it, and I'll try a few problems here if you want to change the base for some reason. Now, I thought, hold on, this. Here's a good example. On the exam Friday, you have log base 3 of 8 times log base A, 8 of 9. Log of 8 base 3 times log of 9 base 8. And you will find the answer. Does that give me an idea? Let me give you a few seconds. See if someone can tell me what's going on here. Why would I bring that example in? And someone may get the answer right fairly quickly. Looks strange. Guys, does anyone think they had the, maybe the answer? Whoa, who said that? Miriam says 2. She says, Professor, it's number 2. Staring at you. Doesn't look like 2 in the raw form you see right now. She says it's merely 2. And what's going on here? Even the original, the log of 8 base 3, I don't know what that is myself. I can estimate here, if this had been log base 3 of 9, just that part, everyone would say 2.
3.
Log of 9 base 3 is 2. If that had been true there. This one, if this part had said log of 64 base 8, everyone would have said what? 2. 8 squared is 64. I didn't have that written like that. Miriam, since you got this, did you apply maybe in your mind, maybe this will change the base? I'm changing bases. Now, can you come up with, Miriam, maybe tell us for the class, what base did you change these to? And we'll rewrite them.
Base 10, log base 10.
Oh, you just want log base 10?
Yeah.
Okay, that's
Log base
okay.
10 of 8.
No problem. You can change it to any base you wish. Now, right now it's log of 8 base 3. She says, no, Professor, I don't want that base. I want base 10. Well, you gotta do this to change it. Log of that new base that she wants, which is B, and she wants a 10. Guys, we'll put 10 in there. Usually it's missing. It's called a common log. In this case, 8. And Miriam, you have to divide that by this formula, log base 10 of what? 3. If I apply the change base formula. Then I think she's going to do the same thing on this one, log of 9 base 8, she's going to change it to base 10 also. Now if I change this one to base 10, here it goes. With the formula, this will be log base 10 of 9 over log base 10 of 8. So far so good, guys? Now you can change that to any base you wish. She chose a base 10, a common log. At this point, did we receive a little help? Yeah, I think these two terms will cancel. That helps me somewhat. And then left over, I see a log of 9 over a log of 3, both base 10. Now, can someone, or Miriam may tell us, Miriam, if you approached it like this, what else did you do from there?
I put it back into the log base A of M.
Oh, you changed it again.
Mm-hmm.
Okay, let me ask you this though. At this point, which I like, does she have everything in terms of a common base 10 in this case?
Yeah.
Now guys, you could have chosen any base. She chose 10. I might suggest on this one, look at this one she gave me here. Could I rewrite log base 10, I'm gonna just leave the 10 off. Could I write that 9 as 3 squared? Just saying the same thing. And then apply the power property, and actually write as the power lifted out here would be 2 log what? 3. Which is still base 10. And by the way, did I have a log base 10 of 3 here? It's still remaining. So I can cancel this out with this after I convert it, and guess what's left? 2. That's one way of many that you could change something to a common base and then work it out. But you gotta be very, very, very careful. And I brought to class today, because I'd forgotten which student it was, maybe Jonathan, in the 2 o'clock session. I says, Professor, I saw this, I think, on the handout, but I didn't quite know how to use it. So you could change to a different base if you wish, since we do wish. Let me see if I did something else with it, maybe that was the only example, I did not. Oh, here we go. Here we go. Another example. Since we're closing this completely down. Let's do this. Log base 2 of x plus log base 4 of x plus log base 8 of x is equal to 11. Solve for x. My students are looking awfully tired. I don't know whether to try to take the class and work and do this and do that and go to the beach and do this and do that. Oh, okay. Give me a few seconds. This is one of my extra credits on one of my old exams. I hope I have it copied down correctly. Someone thinks they have this one. Miriam gave you the answer on 2 for that last one quickly. A little recap. Guys, anyone think they know it? What to replace x by to satisfy that equation? Or about
2 to the power of 11 over 6.
2 raised to the power of 11 over 6. No, hang on. I'm not saying it's wrong. He says, Professor.
No, 11 over 6.
Oh, just 11 over 6?
The 11 is over 6, yeah.
Whoa. 2 raised to this?
Yeah.
You want that? We don't know yet. But you said right here you think it's this. Let's just hope I have it copied down correctly. Okay. No one. Caroline, first thing I notice is they all have different bases. It would be nice if I could convert all of those factors or terms into a common base. Right, everything in terms of just one base. Right now they're all in different bases. Now I like to choose the lowest, if this happens. The lowest base right now is 2. I would like to, if possible, change this one to a base 2. And this one to a base 2. And at least everything would be in terms of 1 log base 2, and maybe that would help me solve it. Guys, with the change of base formula, anyone tell me? Here we go. Here it is. We're going to change the base. I'm going to change the base to a base 2. Guys, just write this as log base 2 of x over log base 2 4. Please tell me, did I apply the formula correctly here? When I changed the base 4 to a base 2. This one, let's change to a base 2. Change the base formula. Log base 2 of x again over log base 2 8. Yes or no? Yeah, at least set it up correctly with the change of base. Ooh, boy, it's quiet today. Caroline.
Could you also write like 2 log of 2 base 2 to the x?
I got you. Let me show you now. I'll show you why. By the way, guys, at this point, far about it. Maybe a strange answer here. We'll see. Who
I was
knows?
wrong, I'm sorry.
Who knows? Base 2, base 2, base 2. At least everything's in terms of base 2 now. If I use my change of base formula correctly. Barbara, I think he's going to change his answer now. Okay, here goes, guys. Step 1, let's call this, leave this first term the way it is. That's fine, it's in base 2. This one we looked at. In this attempt to change a base, the bottom part says log of 4 base 2. I know what that is. You know what that is. This is merely a 2. Isn't it? Log of 4 base 2 is 2. So I can write this as log base 2 of x, all of it merely a 2. Third term, we looked at, the log of 8 base 2 is merely 3. 2 cubed is 8. So it means I can leave this, or write it, as this. I still have it equal to 11. I'm just hoping it'll work. Oh boy, get scared. Okay, so at least everything in terms of a common base 2. That helps some. I don't have it solved yet, but at least everything's in terms of 2. Barbara, did you change your mind?
Yeah.
Oh, you changed it to a different answer.
Yes.
Like what?
64.
You think it's 64? And I heard 32. Hang on. So you're going to say, go ahead and mark this one out?
Yes.
Okay. Okay, I heard 32, 64. I haven't finished it up yet. Now, guys, tell me on the side here, how would you solve this? These are the kids across the street. Okay, do something here with this. It looks a little strange with logs in it, but how would you attempt to actually solve it? Just algebraically. Tell me a way to actually solve this. Is there a common denominator? What, 6? Is there a common denominator involved here? 6?
Yeah.
So I could go through and just multiply everything by 6 to try to clear that out. And if I do, and I'm careful, Professor, I could you do this, multiply everything by 6, both sides. And rewrite this as 6 log base 2x. When I reach the second term, the 2 will cancel into the 6, and I will get a 3 log base 2x. Third term, the 3 will cancel into the 6 to give me a 2 log base 2x. And if I'm careful, the other side's also being multiplied by 6. That becomes 66. Oh my goodness, I'm getting scared here. Is that true? Just cleared it out? Combine like terms, all those terms on the left are alike. They're like terms. Put them together, I think I'm going to end up with 11 of them. Is that true?
Yes.
Divide by 11.
6.
That's a log. Base 2x is equal to 6. And then all of a sudden, when you tell me what that means, just by merely looking at it, by definition, it means at this point what? Base 2 raised to the 6 is equal to x. Here's your answer. Barbad, Congratulations. 64. Now, if you enjoy math, you enjoy this. If you don't enjoy math, I feel for you. But these connections are needed. Are needed. Every student can do it. Every student can do it. Just takes a little practice. So guys, far line and class. Let me go back to the original. We're saying 64 is the answer. Let me go back and replace x by 64 back in the original for a check. That means right here, we think this should be 64. This x should be 64. This x should be 64. Let's do a quick calculation. Log of 64 base 2 is 6. Just mere 6. Next term says log of 64 base 4. 3. 4 cubed. And the last term really says out here, log of 64 base 8. 2. 8 squared. Add them up. There's 11. The checks. Now, do you just randomly try some numbers in your mind and got that to work out, or were you thinking something like this? Something like this?
Let U be like.
Let you be something, maybe creative there, good. Let you be something and then go for it, right? Nice. Okay, guys, let's see what else I had. I'm supposed to be about a half an hour, it's about a half an hour now, on recapping some of this. Do I? Oh, I do have something else, hang on. And then we're gonna need this. Where am I? On the side here, all over the board here. Another example. Here we go. ln e raised to radical 2. I have a group of these on the test, just see if you recognize what to do, and the answer usually comes out to be cute. Guys, the answer on this one is radical 2. You're done. Lots of ways to think of it. You could say, well, power property says I can move this out here if I wish, and have radical 2 times ln of e, and I hope we all recognize that the ln of e is how much? What's the natural log of e where the base is understood, not written to be an e? 1. So it says radical 2 times 1 is radical 2. You're finished. You have it. Let's see if there's something else I should point out. Oh yeah, last one. This one. I'm all concerned about that test. That's why I'm doing this. Log. Oh, why not? This. Over this. And I'm going to ask you to use the properties of logs and rewrite that. Now, does anyone have it in mind? You're using the properties to separate this. Which property, there's only 3 properties, which property might you want to use first? And why?
1/2.
The 1/2, that square root can be represented as what? All that's being raised to 1/2. Now, if I do that, Jonathan, and I have the eraser here so I can do it fairly quickly, so I don't have to rewrite anything. He says, Professor, that large square root is the same as you doing this. And therefore now it's a power, so I can lift that 1/2 out front and have 1/2 log, still got this, over this, like that. Now someone suggests to me, is there somewhere on this where I can use another property? He used the power property. There's also a quotient and a product if anyone sees a way to use it. May I? Which one?
Quotient.
Quotient? I see a quotient. So let's write this as 1/2, leave that 1/2 the way it is. And guys, if I apply the quotient property, and I'm careful, it says log of the numerator subtract log of the denominator. And I give you partial credit for that. Just gonna be patient. Now, do we have some places here we're gonna go further? Does anyone see? By the way, I have not used product property at all. Is there any place in here to use product property? Go for it.
Could you, factor out that difference?
Thank you. It says, Professor, you had better express this in factored form. X subtract 2 times x plus 2. And now, do we have some spots in here where I can apply the product property? And rewrite this as 1/2 is still stuck out front, it's out here. Inside there, guys, the first term with his help there, it's a product. So I can rewrite this as log x subtract 2 plus log x plus 2. That takes care of that. On the end it says subtract. Now be careful. Some brackets here. Is this also a product on the end? By the way, to shorten the work down, you know what's going to happen. We'll separate this as a product. But as I separate it, is there also a power involved? That's an x cubed. So I could use a power property along with that product property. Gotta be careful. Now guys, I'm focusing on this right here. So let's write this as 3 brought out front, log x for the first. Where am I? X cubed and plus what? Log, let me step back and look at it. X subtract 5 and close that up. Let me step back and look at it. Does it look good at that point? Yes or no? Neva, how's that look? So far so good? This end part, especially this end part, right here. Did we get that correct? Okay. All the properties have been used. You just need to clean it up a little bit. And when I say clean it up, I guess I got that 1/2 out front. Guys, you could go through and use the distributive property, distribute that 1/2 on all the terms. You could. And 1/2 here, 1/2 here, minus 3/2 here, and a minus 1/2 here. And let that be your final answer. Make sense? Just distribute that outside 1/2, but all the properties have been used. Whew. Okay, 35 minutes. I won't take 30, I took 35. Now why am I doing this? Professor, why are you going back to chapter 4 again? I thought we were going through chapter 5, your favorite, trig. I am. But I'm concerned about this for all my students. This chapter on logarithms, you know how you guys who are doing your homework, that's a lengthy chapter to begin with. So there's a lot going on there. I don't want anyone to mess up on this. Guys, any concerns here before I erase? Anything at all? Okay. I hope that recap helped. Now I need to get back into the unit circle. This will be a nice change for us. Miriam, could you remind me on that syllabus, which section are we supposed to be in? If I follow this syllabus directly, which section are we supposed to be in today?
5 point something?
5 point something. Does anyone have that point something? Are we in section 5.1, 5.2, 5.3, 5.4? We're in chapter 5, definitely. Who has an idea? Does anyone have the syllabus there?
5.4, 5.5.
Well, let me hear it to me again.
5.4, 5.5.
It says 5.4, 5.5. I got through 5.1 yesterday. So they talked about what, radians? And they gave us us some conversion factors to change from degrees from middle school into this new measure called radians. That's all they did in 5.1. So 8, if I do it, I might be able to get 5.2, 5.3 out of the way at least. Maybe 5.4 touched upon today. Now, with all that said, let me do this. Oh, yes. Guys, we're going to start this as part 1, starting all over. And we're going to go back to this unit circle and do some work with it. I noticed when I started this yesterday, I saw more smiles on faces. I think students who've had a little experience with the unit circle, and most students have, some of them, they'll say, oh, Professor, I remember this. I remember that unit circle and all the parts of that unit circle to work with. Okay, part 1, let's go back to chapter 5. And it's all about this. And this unit circle has a radius of 1. And we talked about it. Now, really take off with this though. I did this. We'll draw a grid and show somewhat what we did yesterday with this so-called unit circle. And extend this a little. As I say, the circle looks something like this. Rough sketch here. I need to take a look at points on this unit circle today based on our conversation from yesterday. We got particular points. Now, keep in mind, this is a unit circle. The radius is supposed to be 1. Of course, I have a center to work with. And guys, since I have it on the grid here, also playing a part here shortly, will be, I have quadrant 1, quadrant 2, so I have to do graphing paper, quadrant 3, quadrant 4. That's going to play a part. Now, since we'll be working with points, coordinates, I need coordinates. Before I jump in and start naming coordinates, can anyone tell me if a point falls in quadrant 1, what are the signs of the x and y coordinates guaranteed if that point is in quadrant 1? Positive and positive. We'll play a part. If I move over to quadrant 2 for middle school, if that point falls in quadrant 2, I'm guaranteed for the x and y coordinates a negative, positive. If it falls down in quadrant 3, I'm guaranteed both coordinates are negative. Quadrant 4, I'm guaranteed positive, negative. All this will play a part. Now let's start naming some of the coordinates. Can anyone tell me this point right here, which is on the x-axis? Everyone label this. What do you think at the very beginning of the unit circle, that point there, what would be the appropriate x and y coordinates based on this is a unit circle? 1, 0. If I go up to this point, the way it looks, it might be appropriate to label this one from that unit circle with coordinates of 0, 1. Like on a sheet of graphing paper. Over here, coordinates of negative 1, 0. Unit circle. Down here, 0, negative 1. No problem. No problem at all. Now, can anyone tell me, I'm going to use a different color here. Can anyone tell me, I put a comma here. I got the point, 1, 0. What angle is that initial point representing as I look at this unit circle? How would you identify what angles involved there? I see the point, but what angle? We're talking about angles. And I'll put in radians. What do you think it is at the very beginning? 0. So we'll call it 0 radians. And its corresponding point is 1, 0. When I reach this point, and they're calling this in your textbook a counterclockwise rotation, So you start on the initial side like this, on the positive end of the x-axis, you move counterclockwise. If I do, of course, I'm gonna make a right angle at this point. Coordinates are 0, 1. Does anyone recall what 90 degrees looks like converted to radians? 5/2. If I go back to the initial and rotate half the circle, semicircle, and end up here. The coordinates are -1, 0, that's from middle school. The angle looks like it's 180 degrees, it's half the circle. Better expressed as pi. Finally, if I go back to the initial, always the initial, move counterclockwise all the way, like a clock, and stop there. From here, all the way around and stop down here. That might be a size of what for an angle?
3 pi/2.
Or 270, exactly 270, or 3 pi/2 in radians. And that's what I want today, this measure to be expressed in radians. Guys, if I go back, one more move here, and move all the way around, and stop at the initial, go right back to where I started. This point could also represent, besides 0, what?
2 pi.
Yeah, 2 pi, or 360 degrees. That's beautiful. Absolutely beautiful. Just marking an angle, a unit circle, representing the coordinates, and I'm good. I know where the coordinates are positive, where the coordinates are negative, and so forth. Now on the side here, let's make a connection to this. On the side here, we have some definitions. I will call this the definitions of the 6 trigonometric functions. Here we are, back to the word functions. 6 trigonometric functions. And there's 6 of these. When I start listing these by name, I guarantee you, probably 98%, not 100% of my students will start recognizing. Professor, I've seen that word before. I've seen it before. Guys, the first one, identified as a trig function, is spelled this way. Sine is abbreviated S-I-N, and then they place the angle next to it that they want you to find that function for. Sine theta. I think I was using a theta yesterday. And that's the first trig function. Its name, sine theta. Now, what's its definition? I'm on the unit circle, you're going to be shocked. These are the shortest definitions you'll ever witness. Not a long, lengthy, wordy thing like you would expect a definition to be. These are definitely short. Sine function, sine theta, definition. Why? Now move on. Number 2, the second trig function, spelling. Spelled this way, cosine, abbreviated, C-O-S, theta. Cosine, abbreviated, and if I say, what's its definition? Not wordy, just a simple remark, statement. It is x. Next one, there's 6 of these, and I know all 6. Number 3, tangent. Abbreviated T-A-N, theta. Definition, very brief, and I think I heard a student say it. Replace y over x. That's the definition for tangent. You can't go wrong with this. Number 4. Pick up next one identified as secant, spelled this way, abbreviated S-E-C-A-N-T. theta. That's another. I have 6 of these altogether. Go on to Stanford, Berkeley, wherever. They have only 6. Secant. Definition? 1 over x. Number 5. Pick up the next one. Cosecant. Spelled this way. Abbreviated. CSC. Theta. Definition? 3. 1 over y. Now, there's one remaining, and some of my students I bet are sitting there, they probably know these. I wouldn't, of course, place it, there's only 6. Does anyone think they know the last one? What's being left out? Maybe, I'm sure you saw this somewhere. Most of us. Cotangent. There's one identified as cotangent. And it's spelled, abbreviated, as a spelling, as C-O-T theta. Definition, simple definition, x over y. I don't care where you look. You're not going to find shorter definitions than those. You're not going to find it. No way. Michael, we're going to do this. I'm going to accept these definitions. I'm scanning through them right now, make sure they're all copied down correctly, they're cute. Look at those little red definitions. Easy, remember. But those are the definitions. Aiden, these definitions apply only to this unit circle. If I get off that unit circle, if that circle is larger or smaller, has a different radius than 1, I've got to modify this. So that's why that unit circle is so important. I think I gave you guys a sketch of it, didn't I, on the handout of the unit circle. That's why that unit circle is so important, because these definitions will hold true only on this. Now, let's see how to apply this on the side. Let's take sine. And it says theta. Let me choose a theta. Theta is the angle. Guys, I'm going to go back. I'm going to try pi over 2. So this is asking sine of pi over 2. Definition says it should be y by definition. So that means I look back at pi over 2, find the y coordinate, it's 1. You're done. That's the sine of 90 degrees. Sine of pi over 2. We try cosine. Cosine, and I think I'll try cosine on, let's try pi in the green. You guys, cosine's definition right next to me says it's merely x. Well, let's look at the x coordinate. The x coordinate over here is -1. That's the answer. You're finished. Let's try tangent. Now we'll try a tangent of, we'll drop down to this one, 3 pi over 2. You guys told me earlier it was 270 in degrees, but 3 pi over 2. And if I try tangent, well, on the side there it says tangent, by definition, if you want it, is placing y over x. That'd be placing what? -1 over 0. Now that one I have an issue. Therefore, the tangent of, I'm trying to 3 pi over 2. Tangent of 3 pi over 2 does not exist. Undefined. Let's use these initials. Does not exist. Let's jump down to secant. Secant of, I think we'll try secant of 2 pi. You guys, I see 2 pi back here on the unit circle. Secant's definition, right next to me in the red, says place 1 over x. Well, the x here is 1. So I'm placing 1 over 1. That one has an answer. cosecant, I'm using the abbreviation CSC. Now, let me go back to maybe 0. I'm shooting these angles at random here. Cosecant of 0, well, in the red it says put 1 over y. Guys, here's 0. So if I place 1 over y, I place a 1 over what? 0. Another undefined. Does not exist. How can you go wrong? And let's try cotangent. And I think I'll go back to maybe cotangent of, let's see what I want here. It might work out nicely for us. Why not? Pi over 2. Let's go back to it. And right next to me in red there, if I want to find it, it says place x over y. Right here is pi over 2. Placing x over y, I'd be placing 0 over 1. And therefore, the cotangent value at pi over 2, 90 degrees, is 0. Could you go wrong? No. How about you can't go wrong? Neva, Aiden, you can't go wrong. Miriam, you can't go wrong. You just can't go wrong in these. Caroline, here's where we could go wrong. This is where my lesson really starts. I'll ask you to find sine, as I was doing earlier. You saw what I was doing here. And my green angle, I'm using green to represent my angle, I want this. And I want an answer. Based on here, it said, well, sine is, by definition, Professor, y. So go back to your unit circle, pull out the y coordinate at pi over 6, and that's the answer. What's the issue? What's the issue? Where's pi over 6? I got 0, 2 pi, pi over 2, pi, 3 pi over 2. I don't see a pi over 6. I've got to place it on the unit circle. It's not there right now. Now, can someone quickly tell me pi over 6, if you're preferring degrees, what size degrees is pi over 6 if you should convert it to degrees? It's 30 degrees. I don't have that marked. I need to mark it. Now I'm going to say 30 degrees is in quadrant 1, of course. But in here somewhere, space here. And I'm going to mark it as pi. I'm going to use degrees for right now. 30 degrees. That's pi over 6. And I'm looking for the coordinates. Right now, guys, right here, let's put it right here. I and you, we don't know what the coordinates are. I gotta find the coordinates and answer that question down there. Now, does anyone have an idea of how to come up with the coordinates at pi over 6, which originally was not on my circle? Anyone tell me? Does anyone have a plan? Go for it.
So you remember the special triangle where you draw out?
Hang on. He's a professor. If you're searching for the coordinates, they're not listed for you like those simple little coordinates 1, 0, 0, 1, negative 1, 0, 0, negative 1. An elementary school child could know those. No, not the next one. 30 degrees or pi over 6, he says, let's be creative. He says, Philip says, Professor, drop a perpendicular down to the x-axis and form a small right triangle. We've got to be creative. By the way, if I'm drawing a right triangle, I've got a 30-degree angle there, I've got 90. That's going to force that top angle to have a measure of 60. Right here. Now, here we go. I know and you know. I'm going to use the word hypotenuse. The hypotenuse is the side opposite the right angle in a right triangle. The hypotenuse is 1. Why can't I go ahead and mark that hypotenuse opposite the right angle as 1 immediately? Isn't that the radius of the circle? and the radius is 1. We're using a unit circle, so it's gotta be a 1. What's missing is this, the x, this, the y. I gotta find them and then place them here for the coordinates. Now, I think Philip's trying to tell me something. He said, Professor, I remember way back in the day somewhere, when I was paying attention in my geometry class, something about a 30-60 right triangle. Oh, I see heads looking, or people looking as though, Professor, I did remember that, but I can't recall right now. Is there something, Professor, special about 30-60 right triangle? There is. No matter how large the triangle is, how small it is, there's something special about it. That's why I need it today. Does anyone remember what was so special about it? That we use so much in math because it's so special. Anyone remember? Anything going on? Okay, let me tell you how I remember it. That's so special. The side opposite the 30-degree angle is always 1/2 the length of the hypotenuse. That means my y over here, which is opposite the 30, should be 1/2 the length of the hypotenuse. And the hypotenuse has a length of 1. That's my radius. So I quickly say, I see this right here, just right like this. This y must be 1/2. Now the x is missing. So after I just use that one relationship, the side opposite to 30 and a 30-60 is always 1/2 the hypotenuse. Anyone tell me a way to come up with the value for the x, and I'll have the triangle I need? Don't tell me, I'm hearing something, I need a name. What should I apply here? Pythagorean what, theorem? C squared is equal to what? A squared plus B squared. Where C was representing the hypotenuse, equals A squared plus B squared. If I apply that right here on this small right triangle, I've got 1 squared hypotenuse squared is equal to, let's say, x squared, plus my 1/2 that I put in there, squared. Hypotenuse squared is equal to the sum of those two squares. Clean this up, this is 1 is equal to x squared plus 1/4. Guys, move that 1/4 over by subtracting, get 3/4. Do a nice little square root. And look how cute that is. That's the x. Radical 3/2. I found it. So now that goes here. Miriam? Now tell the class, if we accept my work, what are the coordinates, the x and y coordinates, for a 30-degree angle?
It's gonna be radical 3/2
Beautiful.
on the 1/2.
That's all I'm looking for. Radical 3/2 and a 1/2. I found them. Now, go on to Stanford, Berkeley, are they going to change? No. No. They're not going to change for a 30-degree angle. It's radical 3/2 for the x and 1/2 for the y. Now let's go over with that done. Now can I answer this question? What's the sine of pi/6? Sine's definition is y. What did we just say, or Miriam just give me for the y? 1/2. So back over here, this is now 1/2. Answer. If you're asked to find cosine of pi/6, my effort over there, cosine's definition right next to me up here is x. And the x coordinate, I think, came out to be radical 3/2. No problem. Tan of pi/6, if I want to find it, the definition there tells me to place y over x. Now, so I do that, I'm placing 1/2 over the x, radical 3/2. Looks awkward, but that's it, y over x. I do see the 2's will cancel. I'll help you out that much. Anyone tell me what that looks like? Simplify. Radical 3/3. If rationalize. Let me go ahead and get the others out of the way. Sine, cosine, tangent, we use the same word right here. Secant. Secant, 5/6. Y and not. Definition says 1 over x. There it goes, that's 1 over, and if you look back to the x was radical 3 over 2. 1 over x. Can someone quickly clean that up for me? You know you can't leave it looking like that. Does anyone know what that looks like cleaned up? Simplified? Whoa, I'm hearing it. 2 radical 3 over, look at that. Thank you. 2 radical 3 over 3. Cleaned up. Next one says cosecant. I'm trying 5 or 6. Definition says if I want it, I gotta place 1 over y. That would be, in my case, placing 1 over 1/2. That I quickly would do, that's 2. And the last one is cotangent. We're doing 5 or 6. And guys, looks like the definition says if I want it, I've got to place x over y. X back there was radical 3 over 2. Y was 1/2. I'll clean this one up for you. The 2's will cancel. It's merely radical 3. Do we accept those? Making sense the way we're approaching it? Where those numbers came from? With the help of the unit circle? Now, the handout I gave you guys yesterday has a copy of the unit circle on it. You say, Professor, can I use that on the test? Well, of course not. But you can look at the unit circle and see that all the values are there you need, except you can't use it on a test or a quiz. I'm showing you where some of the numbers came from. Now, I've got to check my time here. This is nice. This is beautiful presentation. Park, arena. You remember all this? Isn't that cute? That's cute. Now, what's even a little cuter? Part 2. Here we go. I want some relationships here. Aiden, how you doing?
I'm doing good.
Okay. Aiden, I'm gonna do this. I've already done a 30-degree angle. Right here. Focus on a 30-degree angle. I'd like to, with your help, and I gotta watch because my sketch is gonna get all messed up here. I'd like to reflect or move that 30-degree angle over into quadrant 2. Something like this. If I make this work out for me. Okay. Do it. Okay. Let's put it this way. Try to figure it out. Here. Aiden, marker's not gonna work. Here we go. Finally. Aiden, all I'm trying to show in this beautiful sketch is, I'd like for 30 degrees now to be reflected across the y-axis and land in quadrant 2. If I should drop a perpendicular, like I did earlier, and form a small right triangle, something like that. Trying to draw it a little bit better, like that. Do we still have that 60-degree angle involved here in the top? Still have that 60-degree angle is still there. Do you think I still have the same numbers?
Yes, but the sign for the x value.
That's what I want. He said, wait, Professor, go ahead and shift that over. No problem, or reflect it over the y-axis. He says, all you're going to do, Professor, is use those numbers you've already derived over here, but you're in quadrant 2, and from algebra, the x should be negative. That says this should be negative here, it'll be black. Negative radical 3 over 2. And how about the y that was over here? The y stays what? Positive if I'm in quadrant 2. Aiden, is that what you're thinking of? Now, can you tell the class what are the coordinates of this point right here in quadrant 2 based on what we just did?
Negative root 3 over 2, and then comma 1/2.
Thank you. Exactly what I wanted. Those are the coordinates. Now, the bigger question. Here goes. I'm over in quadrant 2. So that angle over there is caught between 90 and 180. It's caught between pi over 2 and pi, which is caught between 90 and 180. That's a fairly good sized angle. Now, can anyone in this clever class tell me? Things are going so smoothly, I don't want to mess this up. From the initial side over to that angle, anyone tell me what size that might be? Tell me, oh, I heard different things. Is it 120?
Yeah.
Okay, let me ask you this. That 30-degree angle I was working with back in quadrant 1 that we did such a beautiful job on, is that right in the corner, right here. So what size is this angle right here? I know that this down here is 30. I just moved it or reflected it over, that's 30. I want to know what the size of the angle, the remaining angle here is. It's not 120. It's 150. Is it 150, guys?
Yeah.
Should both these add up to 180? So is the one I just marked with the arrow there, is that size 150? Okay, so I'm now looking at 150. Farbod, help me out here. Aiden's already told me, label the points, the coordinates, like that. Now, can you tell the class, I'm putting green, I've been using green, what angle, in the green there, and I had 5 or 6 up here, I think it was, 5 or 6. You do that one. Barbara, what's this one represented? What's negative radical 3 over 2, 1/2 is related to what angle?
5 pi over 6.
Beautiful. Give that to me in radians. That's 150. Now I know the coordinates for 150. Or 5 pi over 6. Now we go over and ask, or should run out of space here. Let me go over there. Barbara, thank you. Wow. Here we go. So if you're asked to find the sine of 5 pi over 6, and keep in mind, guys, these definitions do not change. Let me remind you, definition for sine was y, the y coordinate. And Barbara, with your help there, and thank you so much, and Aiden, the y coordinate back here with their help is what? Merely 1/2. And that's the sine. 5 pi over 6. And I could go through and list the others. It's going to take a little time though. But you guys see what's going on? I think pretty soon when I finish this up for the break, if you know 30 pi over 6, the original back here, these coordinates, you'll know the others. I went to quadrant 2. Aiden, come back to you. Let's now move it down to quadrant 3 and see what happens. Now again, I'm going to get this a little messy here, but we'll try it. I'm going down into quadrant 3. Line this up. Okay, guys, that black marker shows up a little bit here, right here.